All right, particle physics, a domain of study which is very hard for me to claim any true knowledge about. But in terms of your exam, I have answered all the questions and written a worksheet for you here from all the past papers. So you got that. That'll be in the link in the description. We'll be going through 3 questions in the video, basically the 3 from the most recent exam of winter 2022. And I also have the theory, fundamental theory. Just like fundamental particles, I have made some fundamental theory, which will aid you to answer all of these questions. We'll run through that right now. Right, so let's talk about this slippery topic. Particle physics. As an overview idea, what we're saying is that to understand reality or the universe, what we need to do is we need to look deeper into it and split it up into smaller and smaller observable parts. That has basically been the mission of physics over the last 100 years. It's done a pretty good job of this. And so that's the idea. So that's the whole point of all of this, is that we're trying to look deeper and deeper into the universe and find smaller and smaller observable parts. And I want to be clear here, this is a model. These are models. And maybe if our model grows, this won't be the case in the future. We don't know. There might be a limitation of the mathematical model or even the actual equipment we're using. Anyway, so let's talk about this theory. So the basic things you need to know. Okay, so we've got these are on your formula sheet. These are some constants which you're going to need to know. You have the speed of light, the elementary charge E, which is plus or minus, be plus or minus U, which is the atomic mass number. These two in particular, E and U, are very important. They're kind of the base charge and base masses for particles, which we use. Because we're talking about very, very small stuff. So these constants are very useful. And the first experiment basically that discovered that how these sort of atoms look was an alpha particle scattering experiment, which basically showed that we have an atom, a basic atomic model that looks like this. We have these things called protons, neutrons, and electrons. And you had this dense nucleus due to the scattering of these alpha particles. Dense nucleus which contained the protons and neutrons, and you had the surrounding electrons which kind of orbit this nucleus. And so that's the basic model, and that's kind of the only model you're going to need right now. And so you have these protons, neutrons, electrons. They have different masses and different charges. Proton has a positive E charge. Electron has a negative E charge. So in terms of an element, you have something like this, which has a nucleon number and a proton number. An element, you've probably seen elements like carbon, helium, argon, all this stuff. These are defined by the construction of their nucleus. So how many protons do they have? So this is this number, the number of protons, and the nucleon number is the number of protons and neutrons. So if you were to want to find the number of neutrons, you just minus A from Z. And also, it's important to know for the standard elements that the protons, the number of protons equals the number of electrons. Now, if we lose or gain electrons, this will be different, and we'll create these things called ions. But now that's just standard. So when you look on that chemical chart that you probably get in chemistry, that you'll get given in chemistry, this is what's going on. So isotopes and ions. So look, in physics, most of the universe, if not all of the universe, is in a process of decay, actually. So it's decaying. I said this before, the universe is actually impermanent. It's always changing. It's actually never constant, which is kind of a weird thing to think about. In terms of isotopes, an isotope is just the same element, but with different neutrons. So like here you have an example, you have the isotope of hydrogen. We've got different neutrons here, but it's the same element. So isotopes will have the same chemical properties, but they'll have different nuclear properties because we have a different nucleus in these different isotopes. And an ion here is, like I said, things are in the process of decay. So if we lose an electron, well, then now we have, because we have the same number of protons and electrons, we lost an electron, well, now we have an excess of positive charge plus E charge now if we've lost one. Well, if we gain one, well, now we have an excess of negative charge. And so this creates an ion. And the most important ion you need to know for this topic is helium 2+, which is the helium ion with a +2 E charge. And this is the alpha particle, because this is just the nucleus of a helium atom with no surrounding electrons, because in actuality, a normal helium atom would have 2 electrons balancing out the charge. Well, the alpha particle is just the nucleus, so we have an extra 2+2E charge. One of the core things that you need to understand for answering these questions, and the most prominent thing in these questions, is radioactive decay. Like I said before, the universe is in a sense a constant transformation or decay. And particle physics or fundamental particles are in this situation is no different. So we have basically 3 main types of decay. We have alpha decay, beta decay, and gamma decay. These are defined by alpha, beta, and gamma particles. Gamma ray. What are alpha and beta particles? Well, what happens is we have a nucleus, or we have an atom, and they have this thing called the strong nuclear force, which basically hold these neutrons and protons together. But as the atom gets larger, what happens is this force gets weaker. They decay. So the proton will change, or something will happen. It will decay because this force between these nucleons are getting weaker as our atoms get larger. That's kind of the thinking around why they decay. And we also have this thing called the weak nuclear force, which is responsible for beta decay. You just need to have a general idea of just what these things are. You don't need too many details. And so for alpha decay, we're decaying alpha particles. For beta decay, we're decaying beta particles. What is an alpha particle? Well, I said before, it's a helium 2+ ion. We'll do questions. There's questions on this. I'll do them. Beta is just a beta particle, and a beta particle is basically an electron or positron, depending on if it's beta minus or beta plus. And this is actually, what they ask on the most is beta decay. And so in terms of beta minus, what's really happening is we have a neutron decaying into a proton and an electron. So it's a neutron, and it's basically transforming into a proton. It happens, we also get the release of a beta minus particle, which is an electron. And that's in order to balance out the charge, because a neutron has 0 charge, and a proton has +E charge, and an electron has -E charge. So it balances out the charge. Charge is always conserved. And with beta plus decay, it's the same thing, but a proton is going to a neutron plus an electron, plus a positron. And it's the same thing. We have a +E charge on the right side and a +E charge for the proton on the left side. And in fact, we also get this thing called a neutrino, which pops out, which I'll talk in a minute. Gamma decay, gamma decay is a bit elusive. It's not actually a particle in a sense, it's just like high frequency electromagnetic radiation. And actually one of the ways that gamma decay happens the most is when we have matter and antimatter annihilating each other. It's very strange. This can just happen, is that we can have matter and antimatter, for example, an electron and positron, coming together, annihilating, disappearing, and turning into these gamma ray photons. Kind of like pockets of energy. Maybe that's a good way to think about it. So in terms of something like beta decay, when these beta particles are released or decay, they have a continuous range of energy, and this is due to the existence of a thing called the neutrino or antineutrino. I actually did a lot of study on neutrinos. I worked for a company that basically worked on neutrinos and understanding them, and they're a very weird particle because they don't actually interact with matter at all, very weakly. So yeah, so this basically showed us that neutrinos existed. Because when the beta particle decays, a certain amount of energy is being given to these neutrinos, which means it's either taking or adding away to the energy given to the beta particle. And so there's a continuous range of energy depending on how much energy is distributed to this neutrino, which previously couldn't be observed. One other thing here, the electron volt. Electron volts are just a way for us to describe very, very small amounts of energy. And so it's just 1.6 times 10 to the negative 19 joules. Sometimes they'll ask you to write things in electrovolts. And in terms of the equations, this is really good. This is basically one of the most important things you're going to need to know is how these equations work. In terms of beta plus and beta minus decay, we have to remember that we have these anti-neutrino and neutrino. That's for the reason I just described before, to balance out this energy, to compensate for this sort of weird continuous energy that these beta particles seem to have. We have to add, we had to find the existence of this neutrino. And finally, fundamental particles. So like I said at the start, the really motivation here is that to understand the universe, we have to go deeper. When we do that, basically we get to rock bottom. It could be a limitation of our model, like I said before, or our equipment, but there is a rock bottom, and these things are called fundamental particles. And these fundamental particles construct the rest of reality. They construct our elements or atoms, our protons or neutrons, these elements. So you could even move further, these construct our, the biology and stuff like that, whatever. But basically we're going as deep as possible, understanding that and building up from there. That's the general idea. So these subatomic particles can be split into two types. You've got hadrons and leptons. Leptons are just electrons and neutrons. These are both fundamental particles, and hadrons are protons and neutrons, and these can be split up into two more types, or called baryons and mesons. And baryon has 3 quarks, and a meson has a quark and an antiquark. These quarks are important, and they are also fundamental particles. And depending on how we place these quarks together, there's many different types of quarks, as you can see here, with many different types of charges. But depending on how we put them together, will define whatever atom or hadron we are constructing. Like for a proton, this will be different than for a neutron, how we place the quarks, because there's basically 3 quarks for baryons and a quark and an antiquark. So there's different ways you can construct different atoms. You've got examples of them here: proton, neutron for baryons, and you've got mesons. There's lots of particles. You can construct them. Basically, all can be constructed through quarks and antiquarks. And that's an example of that here in terms of beta decay. But I'm going to do a question on that anyway. So yeah, that's it. Maybe a little long, but I described as much as I could. But yeah, let's jump into the questions. Okay, so I'm just going to go through all of the questions from the most recent exam sitting, which was winter 2022. There we go. Okay, so a lepton is an example of a fundamental particle. State what is meant by a fundamental particle. Well, like I explained before, a fundamental particle is just basically a particle which cannot be broken down into smaller parts. Basically, it's like rock bottom. We're going to call it rock bottom. So a lambda particles, or this kind of particle, don't get freaked out by these weird symbols. They have to come up with different ways to symbolize these things, because we're running out of symbols at this point. Consists of an up quark and a down quark and a strange quark. Show that the charge in this is 0. Well, if this thing is made up of an up quark, a down quark, and a strange quark, on the worksheet, yeah, you need to look at this table. It's pretty easy to remember, but you have up quarks have +2/3e, strange quark has -1/3e, and a down quark has -1/3e. It's the charge. So the total charge for this thing would be up quark, which is +2/3e coulombs, plus a down quark, which is -1/3e coulombs, plus a strange quark, which is 1. Right, and that will equal to 0. So the charge is 0. This particle is unstable. It decays into a neutron and a pion, shown below. This pion consists of an up quark and an anti-up quark. They bear the properties of an up quark and an anti-up quark. So I'm not sure if I mentioned it, but we have matter and antimatter. And so for all of these quarks in the matter, we also have their anti-quarks. And that's basically all the differences. They have the same mass, the same. So slippery with these words. They have the same mass but different charge. So we could just say, the difference is, they have same masses, but different. I guess opposite, equal, and opposite charge. There's also many other things you could say about it. That's 2 pretty safe bets. And there's 2 marks. Explain why the neutron is classified as a baryon and the pion particle is classified as a meson. Well, this comes down to this. Baryons are made of 3 quarks and mesons are made of a quark and an antiquark. You could say the neutron is made of 3 quarks and the ion, so 3 quarks, so that makes it a baryon, and the pion is made of a quark and quark, not quack, say quack if you want. So it's cool. So see, I was looking through, the reason was not too difficult. Okay, so describe the structure of this atom. Siri, go away. Describe the structure of this atom, uranium. Okay, well, it's basically just asking, what is this atomic structure? Well, we have a proton number, so the number of protons, this is 92. So therefore, the number of electrons will be 92. Formal. Electrons is 92. And if we want the number of protons, not protons, neutrons, this is going to be, if this is the number of protons and electrons, and this is the number of protons, well, the number of neutrons will be 238 minus 92. Yes, I'm using a calculator for that. Not 46. Okay, so that's the structure. Protons, electrons, and neutrons. The decay of this is shown by this equation. For the nucleus, calculate this ratio of X. So we need to identify immediately, well, this is alpha decay. This thing here will be an alpha particle. Why? Because this is decreasing by 4 and this is decreasing by 2. It's not beta decay. Right? In your mind, there should be only 3 ways something can decay: alpha, beta, or gamma. Okay, and so what is an alpha particle? Well, as I described in the worksheet, this is a helium nucleus, which is helium-2+. So it has a charge. The charge of this alpha particle, let Q alpha, is going to be plus 2e coulombs. And the mass of this alpha particle, well, this is going to equal to this thing here. An alpha particle has 4 neutrons and 4 nucleons. So 2 neutrons and 2 protons. And in fact, 0 electrons. And so this is just going to be for U. U being the unified mass unit, unified atomic mass unit. It's the base unit we use for mass particles. These neutrons and protons and all that jazz. So this is kgs. So if we wanted this ratio, it would be charge, which is 2e divided by 4u. So this would just be a half of E over U. This is in kgs and coulombs, which is what they want. Okay, so this is the half of E, which is 1.6 times 10 to the negative 19, divided by 1.66 times 10 to the negative 27. These are just on, they're literally on your exam. E is this, and U is this. Cool. Put all that into your calculator. 18 divided by 1.7 divided by 2. So we round it as 4.8, about 4.8 into the 7. Yep. 4.8 times 10 to the 7. Two particles P and Q consist of 3 quarks. These quarks are up or down quarks. The particle P has no overall charge, and the particle Q has an overall charge of plus 2e. Okay, so what is the quark composition of these things? Well, they're made up of quarks, so they're going to be made up of 3 quarks. They'll be baryons. And so how do we place 3 quarks together up and down to get an overall charge 0? An up quark has a charge of plus 2 over 3e, and a down quark has a charge of minus 1/3 e. So how would we combine it? Well, we'd say U, an up quark, a down quark, and another down quark. This plus 2 of these will give us 0. And for this one, we have an overall charge of plus 2e. So how do we combine these together to get plus 2e? Well, this would just be U, right? 2/3 plus 2/3 plus 2/3 will give us 2. This should be U. Right? Because all these particles are made up of 3 quarks. You just combine these quarks in a certain way to give the charge, the overall charge. Okay, finally we'll do this one. So we've got carbon. It's unstable and it undergoes a beta minus decay, emitting high energy electron and antineutrino to form. So in this kind of decay, write this on here. In this kind of decay, we have a neutron decaying into a proton and electron. You shouldn't need to remember that. That should make sense to you by the balancing of charge, proton numbers here. So we have a neutron. It's changing, transforming into a proton, it's decaying into a proton, plus an electron. Why plus an electron? Well, because this has 0 charge, right? This has plus E charge, and this has minus E charge. There's a balancing of charge. So in terms of this, well, if we want to know, okay, so we have a neutron going to a proton. And by the way, if it was made a plus, it would be a proton going to a neutron plus a positron, which would be, again, there's a balancing of charge. Plus E here, the proton, neutron has 0 charge, and this is a positron, which is just an electron with the equal and opposite charge. This is plus E. We have plus E on this side, plus E on this side. This was 0 on the side, 0 on the side, the balancing the charge. No charge is being lost. Anyway, so we have a neutron going to a proton, which means this number here will stay the same, right? This is the nucleon number. This is the protons and neutrons. If we simply have a neutron changing into a proton, there's no change there. stays the same. However, this is the proton number. We have a neutron go to a proton, then we have an extra proton. And for this electron, be 0 minus 1. This will also conserve these things. So minus 1 plus 7 is 6. 0 plus 14 is 14. And then we have this anti-neutrino here with 0, 0. This is due to the energy distribution, which I showed here. Read through this. This is why we need to look for this thing. State an equation for the beta decay in terms of fundamental particles involved. Well, in terms of the fundamental particles, what do we have going on? We have a neutron. What is the quark construction of a neutron? This is going to get what will give a 0 charge here. Well, it will be a up, down, down. Right? There's notes on this at the end here. Up, down, down, going into a proton. It's a proton. Well, this will be proton has plus E, right? So it will be up, up, down. It's plus 2 over 3e. Both of these, which will give us 1 1/3, and then this is minus 1/3 e, giving an overall charge of plus e. So this goes to a up, up, down. This is our proton, and then plus our electron, and then also plus this anti-neutrino. So these are all the fundamental particles, right? This is what's happening in terms of the fundamental particles involved. Quarks, the electrons, and the neutrino. Use your equation from BI to show charges conserved. Oh, well, I just kind of did that. But, okay, well, this up, down, down, this is going to be overall charge of 0, right? We have the up one, which is plus 2 over 3e, plus minus 1/3 e, plus minus 1/3 e. Right? That gives an overall charge of 0. This neutron. For this one, up, up. Do the same thing, but 2 ups will give us a charge of plus e. 2 over 3 plus 2. Do I have to write it out? Right, and then this thing is going to have a minus e charge. So in terms of charge, it would be 0 on this side, equals to this plus e, this minus e, which is 0 plus, there's no charge on the neutrino or anti-neutrino, and so this is 0. 0 equals 0. Bit overkill, but that's how I do it. Neutrinos were first proposed to exist more than 20 years ago. State an observation about the beta decay that is explained by the existence of neutrinos. Well, this is because emitted state observation about beta decay that is explained by the existence of neutrinos. Well, this is because, like I talked about this before, this is because the emitted beta particles have a continuous range energies, or of more specifically kinetic energies. They're not coming out with the same kinetic energy. Why is this? Suggest how, okay, they're going to ask us why. Suggest how the existence of neutrinos explains this. Why these decay beta particles have a range of energies is due to the fact of these neutrinos taking some of the energy. And so, I guess, how would we word this? Just how this is so total energy is, there's like, how to say it, varying amounts. Yeah, that's probably better. Varying amounts of the total energy in this decay process is Given, distributed, what's the better word? Given to the neutrinos. No, or antineutrinos. Antineutrinos. Jesus. Okay, so you have, a conservation of energy, right? And so varying amounts of energy is being given to the neutrinos, so therefore varying amounts of energy is being given to these beta particles. That's why the energy distribution is continuous. That's it. So there's 3 questions. The worksheet's pretty good. It's actually not too difficult, really, the content here. You just read through this, you have a pretty good idea, and then you can just run through these questions, which is similar, to be honest. But if you do have any extra questions, feel free to ask. And now I'm gonna talk about physics. As this is the last video, I'll talk about what do I really think about physics. In recent years, I've definitely felt my understanding of what is going on in a really big sense in terms of the universe has deepened, and even rapidly, I would say, in recent times. And this has really reconfigured the role that physics plays in my own life and even collectively. I'll give physics some props first. You have there's pretty much no better thing you could be studying in terms of understanding, because physics will give you an understanding of how we think this world around us came about. The ideas in physics is what have sprung to life, modern life, no doubt about it. But I do think that it's very important for us to view physics as a model and not as something that's true. That's kind of the feeling that I've really been setting in. This has been disturbing my kind of experience, because you do thinking that you probably view the world through some sort of scientific materialist frame. This does shape your experience, and as physics starts to fall apart, or we put it in its proper place as a model, then it kind of opens up your experience, and it can actually allow you to see more. I do seem to think that physics claims having this authority where I don't think it really can. And by doing that, it has made us, or given us, permission to dissect and destroy nature, the world. I like this quote, I've forgotten who said it. I'm not sure it really matters, but we've tortured nature for her secrets. It's basically what the business of physics has been doing. It's the business it's in. Literally torturing, cutting into nature to find its secrets. And by placing the natural world in the physics perspective as something that is inanimate, unintelligent, it then allows us to destroy it. It gives us permission. And because of this, we've been unconsciously just destroying everything. That is one of the negative side effects I see about physics. Its current state lacks this spirit and connectiveness. Even though actually all of the physics that we learn, the people that found it or conjured it up, these people had a lot of spirit, yet it's been sort of molded in a direction which is very inhumane, very separate from us. And I like to almost think of physics as a really, really fucking good story. really good. So good that it allows us to move and manipulate and change reality. Shakespeare is written in English, physics is written in mathematics. At the moment, I see mathematics as the biggest set. Physics is being pulled by mathematics. And mathematics is really an intuitional activity if we really get down to it. So the direction of physics, if we don't limit it so much, will be an intuitional activity also. I don't want to bag on it too much, but I have a feeling that we've misused it for our own detriment, and we don't really understand this idea of balance and how it's important that we need to uphold balance in the world. If we just neglect nature and treat it as an unintelligent object which can be manipulated and used for our own benefit, we're going to have problems. Little take on it, on physics. I could speak for hours on physics. So many ideas I have surrounding this, but I thought I'd just sit as we've ended the series and talk about it for a minute. I feel like it's given a little too much props, in a sense, like this glorious thing. In a lot of ways it is glorious, but in a lot of other ways it's actually rather stupid in its approach to reality and to the universe. Physics says it's this thing which desires to understand, but the state in which I see it in now, I feel like it couldn't be far from it. Maybe that's an unpopular opinion, but whatever. Anyway, hope you enjoyed the series overall. Hope you do well in your exams. Hope you have love and beauty in your life. Hope you study hard. Hope you can see the wonder. I hope a lot for you. That's it. Peace out.